So, good evening to all of you, and thank you for coming here for the session. So, as I told, this session is not as a laboratory session, but here we are introducing you with the EC lab resources which we have for hardware instrumentation, test and measurement research. Okay. So, at first we are choosing oscilloscope as an instrument with which we want to start the session, and we may conduct these sessions for most of our lab instruments, so that you at least have an idea that what all instruments are there in the lab and why, when and why we use those instruments, even if you are in CSE. So today that is a very short session of half an hour, where we are going to have some small little introduction about the oscilloscope and its working. So I am Rahul. I am managing all the teaching and research labs here in IIIT-Delhi. And in this session, we are going to cover these discrete points. So, this particular session will cover the use of oscilloscope, types of oscilloscope, basic working concept. We will be familiarized with some of the common key terms. Once you hear this term oscilloscope, so you should be aware of those terms. Then understand basic controls which you can do. And we will do some simple measurements just to have an idea what we learned throughout that session. So before starting, I just want to hear from you if you have heard oscilloscope before. So if yes, then raise your hand. Okay, so it seems no. Okay. Then the next term I want to hear if you have ever heard about a term called sampling. Okay, good to know. Okay, so why oscilloscope? What is this oscilloscope? As by the time you all have seen that what is the instrument which is called oscilloscope. So what happens in nature? We have a lot of signals, right? This light signal, this temperature. There are other signals as you have seen. If you drop some stone on a sea or a river, you will have some sinusoidal waves. Okay, so these are the different kind of signals. So how many kind of signals we have seen majorly? So we all know, right? Type of signal, either alternating or
digital and analog.
Sorry,
Digital and analog.
digital and analog. Correct. Okay, so these kind of signals, just for the visualization. So there are multiple kind of signals, basically analog and digital. And what we are going to do with these signals? So I have some information, but I am not going to. I am unable to interpret it. How would I know that what this signal is providing me as information? So for that I need to see the signal. I need to understand the signal, and for that I need to somehow visualize it. Okay, or it should be understandable to me. So for that we use these electronic instruments which are there to display the signals to you, and these instruments are there to display analog signals. These instruments can display you an electrical signal. Okay, so out of all these signals, how do we convert that to a seeable signal? I want to see it, right? And it can only show electrical signal. So for that, we all know we use sensor which converts any signal into an electrical signal, and that is how we connect it with our DSO. We give this as an input to DSO, and DSO will start displaying it. Fair enough?
Yes.
Okay, so there is this term which is as a black box today. So we say this probe. So these are the wires which you connect from your sensor to DSO to give the input for the electrical signal. So how do you connect your electrical signal to the DSO? So that is with the probes, we say. So we have signal, we want oscilloscope to see it, and what will we do with this? So once you are able to see it, you can do several kind of measurements. For example, you can see what is the voltage of that electrical signal. If that is an signal, then what is the frequency? Is that periodic at all or not? If periodic, then what is the frequency? What is the wavelength? What is the if you are getting a signal from a circuit, so you may want to see whether any of your component is working properly or not. so that you can check if the expected outcome is there. If not, then you are going to judge whether the signal is DC or AC, whether there is a noise in the signal. So noise is another term which is any unwanted component in your signal. So this is really useful for those applications and a lot more. So these are very basic kind of test measurements which you can do once you record a signal. Record a signal on oscilloscope. Okay, great. So once you are recording its signal, you must be interested to know how many types of oscilloscopes are there. So just keeping it very basic, there are two kind of oscilloscope: cathode ray oscilloscope and digital storage oscilloscope. Just forget it at this point of time. So if I define it another way, this is analog oscilloscope and this is, as the name suggests, digital oscilloscope. So the difference is, if you all have seen those CRT screens of TV, might not be oscilloscope, but you have seen the desktops, old desktops and the TV. So those are having cathode ray display unit, which you might have also read in your intermediate somewhere. So these instruments use those screen for the to display the signal. While so what is the advantage there? The signal is interpreted as it is available or present in nature. Okay, so how should I say it? So okay, let me clear it with the second term. Now, the next term is digital storage oscilloscope. And how does it work? It actually so whatever, for example, I talk about natural signal. So these signals are analog in nature, and once you are going to record it, its name suggests that we are going to convert these into digital signal. Okay, so whether a signal is analog or digital, once it will be displayed on digital storage oscilloscope, it will be in digital form. And how do we do that? We are going to see in the subsequent time. So the next form is DPO. Just get aware with this terminology that there is digital phosphor oscilloscope, and this has the capability which is from both CRO and DSO. So you do not need to know much about this at this point of time. You just be aware that CRO we name for analog instrumentation, DSO is a digital instrument. So there are additional names to this. So mixed signal oscilloscope. This has a specific channel. What is channel? Okay, so I told about input. Okay, so these kind of oscilloscope have dedicated input for analog signals and digital signals. What is mixed domain oscilloscope? So these kind of oscilloscope, here we are talking about two different domain, mixed domain, and domain is time domain and frequency domain. Okay, so this is just the additional information which I wanted to let you know since I am discussing the types. So main key point is CRO and DSO, and what we are having here is DSO. Okay. So what DSO is doing? So for me, if there is a electrical signal coming from a socket and I am going to measure it, I should see it as it is. But what DSO is actually doing, though it is showing the signal as it is, let me skip it here. So architecture. Here, while we discuss these things, how DSO is working, we will actually see a very simplistic architecture of DSO. So I say DSO, the full form is digital storage oscilloscope. So the architecture is hidden in the terminology itself. First I say digital. So it means it is somehow converting analog signals into digital signal. And how do you convert that analog signal into digital form? Do you have any idea? So this idea is called sampling, which you people are unaware of. So just to have a brief idea what it is doing here, we have I have it in the slide. So we have a block called ADC. So this is analog to digital converter. So you have this analog signal, but your instrument is digital. So this is actually converting it into digital. And how do we do that? Just a very simple demo of that, for example. So there is a term called sampling, and sampling is how do you draw a sinusoidal wave. For example, this is amplitude, and what is this axis? We all know it, right? So if it is a time domain function, okay. So this is our axis, and what DSO is going to do at, let's say, T1. This is T0. This is T2. This is T3, and so on. This is T n by 2. Okay, half wave form n by 2. So what DSO is going to do? DSO will find out what is the value at T0. Let's hold that. What is the value of T1? It will hold that. What is the value at T2? So this how it will store these values. Similarly for the whole waveform. Now if I have those values at different time intervals, this is called sampling, and its unit is samples per second. So in a second, how many samples this DSO is taking? That is samples per second. Okay. So this is how I get the value, but I haven't digitized it yet. So because there are infinite number of levels. So likewise there are infinite number of time, right? So whatever we have done to the time domain, we will do to the amplitude domain also. So there also we will take certain number of levels, and accordingly we will find out what values we are going to take. So based on this we have information of amplitude and time. For every instance we have an amplitude, and this is how we convert an analog signal into digital domain. Okay, so these your computer will also behave that way. So if you talk for a binary number, so they only know 0 and 1. They don't bother what is happening in between. So kind of that is happening here, but for the higher number of levels. Okay, so we have converted our analog signal into digital signal, and then it says storage. So in storage, what we are doing, we are storing these values. Ultimately we have these discrete components, and I need to display it, okay, somewhere. So storage and processing, the way we want to process. Once we store these values, we process it, we are ready to display it on the oscilloscope screen. So that is the last part which you are seeing, that is screen. So on the screen this signal will be displayed. But since this could be the complete architecture, but here I am adding just one more thing. We have amplitude and time here. So additionally let us add these two things. Vertical, this is not the saved one. So vertical axis control and horizontal axis control to decide how I want to see my signal. So the x-axis and the y-axis. Okay, so we have some controls in oscilloscope which can be controlled for the display of intended signal. So this is the complete architecture from the input till the display in a digital storage oscilloscope. Okay, so what happens in analog oscilloscope, that is CRO, we see the signal as it is. So this signal is only responsible to tune the components in the circuitry, circuitry with discrete components, to somehow ignite the CRT, cathode ray tube, to display the signal. Okay, this is the difference. So this is the very basic architecture. So we are on the same page, right? Any questions by now? So we have seen DSO, types of oscilloscope, analog and digital. We have discussed how digital oscilloscope is actually working. Okay. So once it is finished, let us see our oscilloscope. Okay. So excuse me with this. There is a old slide running. Let me change it now. Can you press leave? Thank you. Yeah, let it be. Okay. So here is the oscilloscope, and you all can see it in front of you. So once we see the oscilloscope, what is the very common thing? The first thing should come into your mind. So there are these three very basic common terms I have taken. So the first thing is channel. So all of you can tell me how many channels are there in your oscilloscope by seeing the actual hardware. So you can find the channels in the red box. Okay. So answer is 2. So we are having 2-channel oscilloscope here in our laboratory. There are versions of oscilloscope where will you find 1, 2 or 4 channels. Okay. So we have a medium one. Then coming out to be the next thing, sample rate. Okay. So we have just learned something about sampling. So that sampling has a unit of samples per second. So this is that sampling rate. So let us revisit. This is an analog signal. My oscilloscope is plotting it by converting it into digital signal. And for that I told you a procedure. I am taking sample. Okay. For example, I took these 2 samples, or maybe 4. So what is happening? Am I going to plot this? Is it? So is this very important factor once you are going to regenerate your analog signal? Is this?
Yes.
No. So who is with no? Okay, and why? So what is the importance of sample rate? Should it be high or low?
It should be dependent on the signal. It should be frequency. Dependent on the frequency.
It should be high. So I am hearing high.
Increase the accuracy.
Accurate conversion होगा.
Accuracy of the signal.
Great. Good sense. Yeah. So as close we go or as high we have the sampling rate, we are going to actually regenerate our actual signal very precisely in a very true form. Okay. So I am not going into detail what all should be the criteria, but giving you a sense that it should be high. You will learn that in your theory classes soon. So what is the sampling rate we have with these oscilloscopes?
Samples per second.
So here, so we have 2 gigasamples per second. Okay, and believe me, this is quite high sampling rate. Okay. Then the next thing is bandwidth. So do you know? Have you heard this term before? Bandwidth.
Yeah.
Okay. And so the only term left is bandwidth here. Okay. And this oscilloscope has 70 megahertz of bandwidth. But what is the significance of it? Yes. So you are pretty late. We are ending the session. Maybe next time. How it sounds. If we meet next time. Huh? Please. थोड़ी देर, we don't have enough oscilloscopes now. Okay. So the only term left here is bandwidth. So likewise we discussed about sampling rate. Now the next term is bandwidth, and this bandwidth actually governs what is the importance of bandwidth. It is actually very costly item. So the bandwidth here always starts from DC. कौन आएगा भाई यार? बाहर है ना?
Govind.
Okay, so coming back to this, so 70 megahertz. So this oscilloscope is telling you that, see, I have a bandwidth of 70 megahertz, and this means you can trust me for the measurement of signals up to 70 megahertz of bandwidth. So that is the frequency of the signal. For example, this is 1 by 2 f, I believe, right? So if it is the complete time, it is 1 by f. So it says you can believe me if you have a frequency of 70 megahertz of your input signal, I can accurately display it. But what happens, let me give you a little clue. So the complete input chain to this oscilloscope with this channel act as a low pass filter, and we all have seen the frequency response of low pass filter, have we? Low pass filter, amplitude versus frequency. Do we know low pass filter? Have you heard low pass filter before? Filter? Don't we know? Okay. So what filter does, as its name sounds, filters the things off. So here, if it is saying 70 megahertz, so I have some amplitude. You people know frequency domain and time domain signals? Have you heard frequency domain thing before? AC signal analysis? Not yet? Okay. Then this is too much for you. So what happens? What is the frequency of our power supply? Means the home power supply. 50 hertz, right? So likewise, we have signals of various frequencies, not only frequency. For example, you purchase your mobile, right? What is the frequency of that oscillator? What is that? Oscillator, that crystal oscillator, that clock frequency. You see, no, how many gigahertz of your speed of your system? 1.8 gigahertz, 2.4 gigahertz for this desktop. So that is the clock frequency. So these are the frequency things which we actually work with in real time. You know 5G is coming. We are using 4G, right? So what is the frequency, at what frequency 4G operates?
10.
No, it is into gigahertz. So these are the frequency ranges I am just telling you, from 50 hertz to gigahertz. And so this oscilloscope can measure a signal up to 70 megahertz only. Seems very less, but it is quite useful for the laboratory stuff. So so if what happens in actual sense, so since we are not discussing in detail, let me tell you in a very layman term, just consider it as a thumb rule. If an oscilloscope is of 70 megahertz, we can very accurately and precisely measure a signal up to 1/5 of this bandwidth. So 5, what is the value? 70 by 5.
14.
So we can measure a signal. It is kind of thumb rule in test and measurement industry, okay? So we have a reason for it, but maybe the next year. So we now know. So now if you go into any lab anywhere, if you see the oscilloscope, you know the basic terminology with which you can at least analyze whether this lab has a good oscilloscope or not. Okay, so this you can consider this as a good. This is the benchmark, you know. So I am not discussing this with you. Okay, so we have discussed the oscilloscope. Now coming to that beautiful screen which will help us in the measurement. So this is the screen. If you switch on your oscilloscope, can you all switch on your oscilloscope? So there is a button in the left here, here somewhere on the leftmost.
Left corner, left arm, you can see the sign, power sign there. Power button is there, you can press that button and switch.
So you all switch on oscilloscope and you will see this nice screen in front of you with some kind of line or deviation or anything. So while oscilloscope is taking time to switch on, let us discuss a few key points. So the first thing what I observe is these two different lines. So this is the actual input signal which is applied to the input. So we have two channel oscilloscope. So these are two different lines. And how do I know it? The color coding is done. So the first channel is of yellow, the second channel is of green. So you can see on your screen, if it is switched on, you will find these two numbers. So these are for two different channels, channel 1 and channel 2. Or most of you by default will be seeing the signal from channel 1 only. You might not be seeing the channel 2 because your channel 2 is not on. So we'll see how to switch it on. Let it be for now and focus on this term. The first channel is showing 1 volt. So what is this 1 volt? What is this signifying? Is this the amplitude of this waveform? So here it is not. You can see x-axis and y-axis, and we talked about it. Oscilloscope is displaying a signal in time domain. So the x-axis is
Time.
y-axis is amplitude. Okay. So once I say this is time, this is amplitude. How should I measure this signal? What is the, for example, we discussed what is the amplitude and what is the frequency, all those kind of things. So here you all can see in your oscilloscope screen, this is further divided like this, is it? Yeah, so we say this as a grid. The next term, grid. So what this grid does, this will help us in the measurement. So you see here 1 volt. If it is 1 volt here, since this is for voltage, this says 1 volt per division. So this is 1 volt. This grid height is 1 volt. 1 volt per division. Similarly, you ignore this. Here it says 50, for example, microsecond to me. So likewise, this is for time. So this provides you the value of time axis, grid on time axis. So 50 microsecond per division. So what is the advantage if I know this height and this width? Yeah. So now based on the number of grids, I can measure the amplitude of my waveform, and based on the time domain information, this time axis, I will compute what is the time period or the frequency of the signal. Is it? So that is why these grids are helpful. There are some additional settings. If you want to see this signal, have you heard? Okay, let me tell you. So I have some signal sine t. Is this the current plotting for sine t, where A is sine t? Maybe A is amplitude. I cannot have x. So A is equals to x. Is it? So what will happen if I add 2? How should I plot it?
ऊपर shift.
ऊपर shift हो जाएगा. Okay. So this is called offset, and this term here mentions the offset in time domain. So likewise, you are shifting it here, you are also shifting it here. then how would I know the vertical domain offset? So this is the marker there which will show you vertical time offset. So you all might be seeing it at the center right now. So if it is different setting for some of you, then that's okay. Okay, na? Okay. So, is there any other information on the screen? So, today I am not discussing this thing. So, for the basic measurements which are planned for today, you must be aware with these things. Okay, there is one very important thing, trigger. So, this trigger I am not discussing. So, please excuse me today for this because this will be too much if I discuss. So somehow I told you that if I am able to see the waveform, I will be able to compute do the initial measurement, which is time domain and frequency domain. Okay, don't worry, we will discuss trigger next time for sure because time is exceeding. So the next thing is I have discussed about some controls. So these vertical axis time division setting and vertical division setting, those amplitude division setting. So you can control this from here. Let us talk about this vertical here. You all can see on your oscilloscope. So this is the knob which is going to change that per division setting. So all of you can move this knob which corresponds to first channel. So this section corresponds to second channel. This is for the first channel. If you move this knob, you will see that voltage per division is changing. So you see on the top the first with first channel. If you rotate the knob, you will see the change. Is it happening? Okay, great. So this is for the offset. If you rotate this, you will see that offset will change for that wave, whatever line is on your oscilloscope. So you can give the offset. Changing?
Yes.
Changing for all, right? So we are aware with this section. Now coming out to horizontal section. So in horizontal, you can move this for time domain setting. So if you see at what location I have told you to see that time domain setting, time division setting. So just rotate this knob and see if the time division setting is changing. It must be changing. And you can rotate this to see that offset in time domain is changing now. Changing? Great. Okay, so there are some additional things like trigger and those measurements which are not the very basic measurements. So I am not talking about this right now. Let me talk about this term here. So you all can see run, stop. Let me move the slide further. So you have these four terms: default setup, auto scale, run, stop, single. So run, stop and single, what happens? Your oscilloscope is capturing waveform. Okay. So if you want to do further measurement, you can stop it from the acquisition. So it is a device which is acquiring signal. If you want to stop that acquisition and focus on the screen right now, whatever you are seeing, you can stop it. It will stop the further iterations of taking the signal as input. Okay. So these two buttons do the same job at this point of time. We will not discuss what is the difference. That is very minute. We will discuss it later. Then the next thing is default setup. So as the name suggests, can you have some idea? Default setup. So at first, once you sit on your oscilloscope, you are going to press this button before any test and measurement. Because the guy who was working with this oscilloscope before might have done several changes. So just to bring it to the default setting, you simply press it and then start working on your measurement. Then auto scale. So this is the beauty which is available with the digital storage oscilloscope and not analog CRO. Since you have information about the signal you have taken the samples and recorded in storage box, and now storage box can do the processing. So once you being CSE or in ECE and working with microcontrollers, you know once you have the data you can do lot more things. So that is what is this device is able to do. Once it has the data, it is saying you push auto scale. What I will do, I will capture the signal, get the complete information about the signal, and then try to visualize it over the screen based on my understanding. If it is not correct, it might not be correct every time, but it will save some of the initial time once you start playing with these buttons. So this will automatically do that. What it does, so you have this sinusoidal as the input. Now on your screen right now, for example, you are getting this line. So what can be the possible cause? You might not have adjusted the vertical division setting so that to see this signal this way. Is it possible, right? You can, so instead of this, there can be another situation like this. Okay, and so on. So this is not separated apart. So for example, you have done the correct voltage setting and it is like this, but it might not necessarily be plotting like this and will be plotting like this. Okay, so then you need to adjust the time division setting. So this auto scale, by sensing the signal, can do this. And one last thing, once you do the measurement, so by this you must be pretty clear that what I am trying to do is utilizing the full screen. For example, if you have a sinusoidal wave, you are expected to utilize the full screen. And what are the advantages of this? Why should I do this? Any idea?
So more.
Any vague idea?
More the sample spaces. Accurate sample spaces.
Yeah, exactly, somehow. So once you are going to do the measurement, you are actually counting the grids per division, right? So the more fine details, the more you will zoom, the more detail you can find out. Okay, so for example, a wave is crossing like this. So somebody says it is half, somebody says it is 0.45. So this will only be clear once you will have the full possibility of zooming it out. Okay, so the maximum we can make it clear. So these are the initial things for the measurement. So though you do not know the complete thing, but the very basic understanding for your initial measurement. So there is this for further study. It is not like we don't have topics. So as I said, trigger is pending for next session. So we have multiple topics to discuss more about the oscilloscope. It is not very small thing, and so the time is limited. So thanks, and with this thanks, there is one kind of activity which you will have to do. So we have an unknown signal. So you will see in the oscilloscope there are two channels. There is one more thing from which a probe is connected and the signal is coming out. So this is the red, this is black. So you will connect it that way. So for some guys it might be white. And then so you connect it on the breadboard. Then you have a resistive network. These resistors are equal. And then you have to check the voltage across this resistor. The resistor and ground. So for that you are having this probe which we haven't discussed. For this probe, just be aware that this is the signal probe. So you will connect this thing here. This is the signal probe. This black wire is for ground. So you will connect it to the ground. So once you connect it, start doing the measurement. You must expect some waveform on your oscilloscope, and what all you have to do, you have to do these three things and inform. So you have to find out signal type, what is the peak to peak voltage, and what is the frequency of that signal. So you all are having this kind of probe coming out from the left side channel. So this is from the signal source, and you are connecting this end towards the ground, this end towards your resistor. Okay. This is the we are having a see it like
अच्छा ये रजिस्टर है
so I told you that how come I know? So I know from the way in this table. I know what is this wire. Based on the circuit I have given, so if you connect it other way, then yeah, it will be the same.
You can work. Excuse me.
So this is the kind of breadboard you have. You will have to connect the red cable. You will connect the black cable like this. Then the signal thing, this particular end should be connected here, and the rest of this thing, black cable, should be connected to this ground, which is shorting to this black from the source. This signal probe has a pin for some of you, so be very careful. Your pin should not be damaged. It will damage the cable. You just touch it here. Yeah, and here. There is a junction of those. Right? Signal.
Excuse me.
So this is the signal probe.
You have to connect this resistor in series. First connect this in series. So in the diagram you can see now both of those are connected in series. Connect it in series, and then that V out, you see that V out. Using probe you have to measure that V out. Yeah, red one is.
So how do we input? How do I input the red in red code?
You have to connect. This is what is terminal. You don't use what to So this black wire, since this is ground, this is signal, so this should be shorted to ground. These two are ground, so you can connect it single. So here, ground.
This is the ground.
This signal is connected between these two resistors.